So in my talk, I will generalize enumerative properties of the lattice of non-crossing partitions. I will start with classical known enumerative properties. I will talk about the new core label order and introduce new parking functions. And at the end, we will see our two main theorems. So let us consider non-crossing partitions. First, we can compute the Möbius function, and the Möbius function of the lattice of non-crossing partitions is given up to the sign by Catalan numbers, which also count the number of unique dict-paths. I've illustrated them here. And that's my first enumerative property we are going to generalize. Next, number of maximal chains in the lattice of non-crossing partitions is given by parking functions. I've illustrated the parking functions as labeled dict-paths here. And we can do something much more general. We can count multi-chains. And the number of multi-chains in the lattice of non-crossing partitions is given by Catalan numbers. Now we have seen a generalization of the lattice of non-crossing partitions for any Coxeter group and a Coxeter element C. And by Nathan reading, we can study non-crossing partitions using core label order, because we know that the lattice of non-crossing partitions is isomorphic to the core label order of the Tamari lattice. This brings me to the goal of my presentation. Can we generalize these enumerative properties of the lattice of non-crossing partitions? For this, I'm going to talk about the core label order. And before introducing core label order, I will define an edge labeling. We have seen this from Emily yesterday, but I will review and go through it. So we are having a finite semi-distributive lattice, and the joint irreducible elements of the lattice are exactly the elements that have a unique down cover. So in this case, J is a joint irreducible one, then it has exactly one down cover. I'm writing them as J down. And for any cover X covered by Y, there is now a unique joint irreducible element such that when I'm taking the joint between the joint irreducible one J and X, I get Y. And when I take the meet between J and X, I get the down cover of J. And then I'm labeling the edge, the cover relation X covered by Y, by the joint irreducible element. So here's an example of a of this edge labeling, but that's a nice example for me because this one is not a Tamari lattice, but it is a semi-distributive lattice. So we can do this edge labeling. For the joint irreducible ones, the edge is labeled by the joint irreducible element. And for example, the edge B to D is labeled by an A, because when I consider A and B, the meet is exactly the 0 element, which is the down cover of A. And when I take the joint between A and B, I'm getting B. So this is the edge labeling for this semi-distributive lattice. Now, I will give you the definition of the core label order. So the nucleus of a lattice element, I will start with the nucleus of a lattice element is the meet of all down covers of this lattice element. Then the core of an element is exactly the interval between the interval of the nucleus and the element. Then the core label set is the set of all edge labels that appear in the core. And the core label order of our semi-distributive lattice is exactly the poset of core label sets ordered by inclusion. So let us do an example. So I'm again considering our example from before, and I will identify elements by their co-label sets. So I'm getting in the co-label order a cover relation from the smallest element, 0, to the joint irreducible ones. And what about D? For D, I'm considering now the down covers, which are C and B, and I'm computing their mean, which is in this case 0. Now, so here is from bottom to top up to inclusion of the core level sets. So for example, you're having here the 0 element, which has no lower cover. So it's going like the arcs. From here to here is the lattice. Yeah, right. For D, I have the core label set where I'm collecting all these edge labels. So I have here A, B, C, and therefore I'm getting a cover relation in the core label order from A, B, and C up to D. I can do the same for the biggest, for the 1. I'm computing the mean, and then this one is our first example of the core label order. Now, again, remember, we want to generalize enumerative properties of the lattice of non-crossing partitions. And I'm going to do this in the context of v-Tamari lattices. So what are v-Tamari lattices? So v-Tamari lattice is the rotation lattice of new trees, where these new trees are constructed as I'm embedding a binary tree in the Ferris diagram. Formally, I say 2 nodes in the Ferris diagram are new incompatible if one is northeast or southwest to the other one, and I'm taking a maximal collection of new compatible lattice points, weakly above my new. And then I say a rotation is a move like illustrated here. I have an element which is a value like this, and Q has something to the right and something above, and then I'm rotating Q in a way that now R is below Q and P is to the left of Q. So that's a rotation. Maybe to get some ideas how these lattices look like. This is an example of a v-Tamari lattice. I'm having here again my bottom element, and here is the top element for me. And just to a short remark, this rotation sense. So I can rotate the easiest way, I can rotate over one box, which will be this line, but I can also do rotations over more boxes. So, and these lattices are semi-distributive, and I can consider the core level order of them. So let us do it for our example. So I've done the example here, and this one is done the core level order. And as you see, the core level order is not necessarily a lattice, but it is always a semi-lattice. And what I'm doing now, to remind, we had this, and we want to count, and we want to compute Möbius functions. So let us do the same again. I'm computing now the Möbius function between the bottom element and one top element. I can do this for all the top elements. And then I'm taking the sum of them. At the end, for the sum of these Möbius functions, I'm getting here a 7. And when I count the maximal chains in the core level order, I'm doing also counting. I'm getting here a 12. Now, when you are considering, when you're thinking, I said we are going to do this for v-Tamari lattices. So the important thing for the nu-Tamari lattice is the lattice path. So when I know my lattice path, they are usually in biaction with new trees. And when I know the new tree, I can compute the complete nu-Tamari lattice. And I can compute the complete core-level order of this nu-Tamari lattice. Yes. I'm summing up so the Möbius function from the 0 element to alpha. This one is the 1. The next one is, so in this, the next, overall maximal elements. Okay, so, yeah, so can have more elements on the top. And in this case, we're only having like 2 levels, so you can easily check. Yes, and then I'm taking the sum of all. So what I wanted to say is, when I know my lattice path, I can do all these computations. So what about doing it directly only with my lattice path? And this brings me to the point I want to introduce new parking functions. For new parking functions, I will introduce them by labeled dict paths. So that's the same idea, because we know parking functions, and I'm doing the same. Formally, for our counting, I will introduce nu down, which is the path obtained by my original lattice path, but I'm deleting all letters of the lattice path up to the first is step. So in this example, we have seen before, in our example, I'm deleting the first is step. And then I'm defining nu down as the rest of my lattice path. And I'm counting again. So I'm counting the dict paths. I'm getting 7 nu down dict paths. And I'm getting, so for parking functions, I'm counting some of them twice. And when I sum up, I'm getting in total 12 parking functions. This is our first main theorem. So for having a lattice path with no consecutive north steps, we have that the sum of the Möbius functions is given up to the sign by the number of nu down dict paths and the number of maximal chains in the core level order of the Tamari lattice is given by the number of parking functions. So just to have this in mind, at parking functions, some of them I've counted twice. So there is a labeling, so you can really think of them as labeled dict paths. And when I'm counting this labeled dict paths, I'm getting maximal chains in my new core label order. And when I forget about the labeling, I'm obtaining the sum of the Möbius functions. So this is our generalization of the first two enumerative properties. And what about the third one? We wanted to count multi-chains. And for multi-chains, now we introduce some like a new multiplication of a lattice path. So first, only think about these two pictures maybe. So again, say this is my dict path, and I say for an integer k nu is then the dict path obtained by nu, where I multiply the number of east steps. I don't care about the north steps. I'm only multiplying the appearance of east steps. So at my original nu, I had 1 and 2 east steps. Then 2 nu is going to have 2 east steps and 4 east steps, and 3 nu is going to have 3 east steps and 6. And our second main theorem gives us that we can count the dict paths of this k nu lattice paths to obtain the number of k multi-chains. So again, we need the condition that our lattice path has no consecutive north steps, and then the number of k multi-chains in the new co-label order is given by the number of k nu dict paths. So it is enough to count them here, the dict paths, to obtain multi-chains in the new co-label order. And so these were our generalizations. Then the theorem does not hold. There are happening many things, and so everything works for having the case no consecutive north steps. There is super nice results in combinatorics for this case. If anybody has ideas for handling this case, I'm open-minded. And so these are our generalizations. And what we can do is we can consider a special type of nu, so a particular form of lattice path. And this brings me to the point of v-Tamari lattices, because v-Tamari lattices are the rotation lattice of a nu tree of the form north east to the power of m, and this one to the power of n, where this one is really to the power. So I have these blocks more often after each other. And there are canonical realizations or different realizations of these v-Tamari lattices. I have some 3D models if you're interested. So you can have a look in the coffee break at the 3D models. They are the canonical realization. And you can have a look and you can count. We find some Catalan numbers there. But now let us consider what happens if I'm considering the new label order of an v-Tamari lattice. For this case, we obtain beautiful numbers. So these beautiful numbers already appeared in some presentations yesterday. For example, the sum of the Möbius functions in the co-label order is now given up to the sign, this number, which we have seen by Christian Stumpf and Christian Grattenthaler, which was counting positive m-divisible non-crossing partitions in type A. And for example, the second one, when we are counting maximal chains, this one is the classical parking function times m to the power of n. So there we are getting super beautiful numbers, which are special cases of much more general formulas. Now the interesting point is we obtain, so by Armstrong, the same numbers hold for the lattice, so the poset of m-divisible non-crossing partitions, but our result is different because the co-label order of the v-Tamari lattice is not isomorphic to the poset of m-divisible non-crossing partitions. As you can see here in the co-label order, there appears one node that has only one upper cover, which does not appear on the right-hand side. So they are not isomorphic, but we obtained the same numbers. The results with counting maximal chains and counting, yes. So as a short summary, at the beginning, we had these enumerative properties where appeared Catalan numbers and parking functions. And in our generalization, we are counting up to the sign nu down dict paths and nu down parking functions. For the case having m-Tamari, we obtain beautiful numbers. And for counting multi-chains, where the classical result is given is the answer by Catalan, we now only count the number of k-nu paths. So these are our results. And that's my presentation. Thank you. You mean cross-Tamari or something? Yeah. That's a natural question. We have not considered them yet, but it's a good point for the next steps. No, we're living in Taipei. Yes, that's no problem. So, for example, we can, if you give me the lattice path, it's completely clear what is the sign. So the Möbius function is computing placing a 1 here, and then you can think of them geometrically as the joint irreducible ones as edges, and then you would obtain here minus signs, and at the top you're getting a plus sign. So it depends on the number of north steps that appear, or if you want, so the dimension of the maximal polytopic part, and then you can, yeah, the exact formulation is exactly describes the sign.